Hi, everybody. This is Monique Morton coming to you live from our offices here in Lexington, Kentucky. And I am presenting the next to last in a series of videos for Advanced Kentucky's office hours. In this case, my topic is about convergence of series. I'm going to be looking at a series of constants first, and then I'm going to be looking at intervals of convergence. We're going to go over how to solve some problems using multiple choice questions and parts of free response questions. It's important to note here that the series questions tend to be on the no calculator portion of the exam, simply because calculators with computer algebra systems have series functions built in, and we don't want to create a situation where a student has an advantage because of a certain type of calculator. So most of the series questions, Taylor polynomials, endpoints, intervals of convergence, everything under that category is usually going to be on the no calculator portion of the test. So let's start by looking at a few things. I'm going to go ahead and screen share now on test for convergence. So focusing first on series of constants, I would recommend determining whether the series of constants converges or diverges based on this order. So the first thing I suggest you do is to do the nth term test. The nth term test is quick. You can do that almost in your head. If the limit of the n goes to infinity of the nth term is not zero, the series diverges and there's nothing else that you need to do. Now, assuming that this doesn't happen and a series may converge, nth term test is a test for divergence, not convergence. So it can't tell you it does converge, but it can tell you that it definitely does diverge. You're going to hope that you have one of three special types of functions. The first one is the alternating series. So you have signs that are alternating: positive, negative, positive, negative, positive, negative, or negative, positive, negative, positive, negative, positive. If the signs are strictly alternating, if the terms are strictly decreasing in absolute value, that is, if you ignore the signs, are the terms decreasing? And if the limit then goes to infinity of the absolute value of the nth term is zero, then you know that the series converges. This is a test for convergence. It is not a test for divergence. So if you don't have enough information, if those three conditions are not met, you don't know whether it converges or diverges. So don't worry about the stuff about the limit. If it's not an alternating series, you're going to hope that it's a geometric series. Now, hopefully you learned about geometric series before you got into AP Calculus. Geometric series are a constant times some kind of common ratio, and you know that that geometric series converges if and only if the absolute value of r is less than 1. Now, in this case, if the absolute value of r is not less than 1, that is greater than or equal to 1, you know that that geometric series diverges. So this is an if and only if case, so it actually goes both ways, and if either part is not true, both parts are not true. Now, if it's not a geometric series, you're going to hope that it's a p-series. Okay? A p-series is of the form 1 over n to the p. Right? This p here is an exponent. Okay? If your p-series is of that form and that p is greater than 1, it converges, and if p is less than 1, the p-series diverges. If p is equal to 1, you have a special case that we call the harmonic series, and the harmonic series diverges. You just need to remember that. You talk to your teacher about why that is, but the harmonic series, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc., diverges. Now, if it's not one of the three special types, now you're going to go into some other tests. And one of those tests might be the integral test. I choose to do the integral test if I change the nth term to be something that as a function of x that looks pretty much like that nth term, and it's something that I think I can integrate fairly easily, then I'm going to do the integral test. I'm going to compare the infinite series to an improper integral. If the integral converges, so does the series. If the interval diverges, so does the series, and vice versa for both cases are true. Now, here, this only works if all of the terms are positive. So beware of anything that's alternating. If it's negative, you can factor the negative sign out to find out whether the positive series converges or diverges, and then the opposite of the series will. After the integral test, another one of those tests that you may try to use to determine convergence or divergence of a series of constants is the ratio test. This works just like the ratio test does when we do intervals of convergence. Absolutely convergent, divergent, and this is actually equal to 1. It kind of looks kind of like the equal sign isn't projecting very well. If the limit is greater than 1, it diverges. If it's equal to 1, it converges. And if it's if it's less than 1, it converges. And if it's greater than 1, the limit that is, the test fails and you might have to do something else. I really don't do the ratio test for constants very often. So do with that information what you will. The last two tests that you should know in terms of testing for a series of constants are both comparison tests. The direct comparison test, if you can compare if you're bound above by another series. So what you're saying is this, right? If I have a series, let's say the nth term is a to the n, and that series is always greater than the series for b sub n, where b sub n is the nth term of the other series, then if the greater one converges, then so must the lesser one, if they're always greater than. If the top is bounded above, then the bottom has to be bounded above as well. And the other way around, so if I have a smaller series, let's call it a sub n, and it's always smaller than b sub n, where b sub n is the nth term, then if the first series diverges, if the lesser series diverges, if the other one's always greater, then it has to diverge too. The bottom one can't be unbounded if it's always less than, and the top one be bounded. That's just not going to work. I actually quite like the direct comparison test. And finally, the last test here is the limits comparison test. And basically, you're going to use two nth terms from two limits. Now, sometimes students wonder how I am going to determine what to pick. Well, what I'm going to pick is I'm going to pick a P-series, a geometric series, or an alternating series that I know how to tell whether it's convergent or divergent or not. And when I compare the series I have with one of those series that I can easily determine convergence or divergence, then if the limit here is a positive real number, then either both series converges or both series diverges. So if I pick the series with nth term f of n, and I'm trying to test a series with nth term g of n, if the limit as it approaches infinity of the ratio of those two functions is a positive number, then if I knew the first one converged, now the second one converged. If I knew the first one diverged, now the second one diverges. If the limit is 0 and the bottom one converges, then the top one converges too. And if the limit is infinity and the bottom one diverges, then f of n diverges too. So I'm going to use the denominator to put the limit that I know or can easily find, and then put the one that I'm testing as f of n. So what we're going to do now is we're going to look at a bunch of multiple choice questions. The first thing I'm going to point out, though, that if you have the handout that I provided to teachers in AdvanceKentucky, you should have this flow chart, which pretty much summarizes all of the tests I just talked about. Right? First, do the nth term test. If the limit is equal to 0, it could be convergent, so you keep going. If it's not equal to 0, you stop, the series diverges. Then you look at these three together. Is it a geometric series, a P-series, or an alternating series? If it's one of these three, then you do the corresponding test determines convergence or divergence, and you'll know that right away. If it's none of these three, then you go down to the ones at the bottom, the integral test and the comparison test. The ratio test isn't in here because, again, I really don't use the ratio test to test series of constants. So it's not in my flowchart. And I only had room to put the direct comparison test. I didn't put the limit comparison test, but the comparison test here could be either, that's why there's a star for me to remember. It could be either the direct comparison test, which is what you see here, or the limit comparison test. Right? So integral test, comparison test, those are all kind of on the same level, and it's what you do if none of the stuff above works. So looking at some multiple choice questions. I'm trying to make sure I have the right page now. Oh, here it is. And something to write on. Let's talk about this first question. Now, number one, it wants to know for what integer k, where k is greater than 1, will both of these series converge, right? Now, this first series, I'm actually going to do the second one first. It just helps me when I do this problem, and I immediately recognize that that second one is geometric. So what I'm going to do here is I'm going to say the following. I'm afraid my marker might bleed, so putting some extra paper in between here. So what I'm going to say is the following. So if this in this second series, in this series, right, this is geometric. And geometric series converges if the absolute value of the common ratio, in this case, k over 4. Now, since k is greater than 1, I already know it's going to be positive, is less than 1. Okay? So it converges when k over 4 is less than 1, which means that k must be less than 4. Well, looking at my choices now, I can immediately eliminate A, B, and C, right? Because none of those numbers are less than 4. So now I look back over here at the other series, and it looks like because of this -1 raised to a power, it'll probably be alternating, but it's only going to alternate in certain cases, right? This does not alternate if k is even, right? It doesn't alternate if k is even. And if you think about that, if k is even, that means this power is always even, which means if I take -1 to an even power, it's now positive. Okay? And there's a harmonic series which diverges. So it does alternate, however, if k is odd. And if k is odd, we'll have what we call the alternating harmonic series. The alternating harmonic series, which I'm just going to tell you that the alternating harmonic series converges. So if I want the k for both of them to converge, two things must be true. K must be less than 4, and k must be odd. So that means that the answer to this question then must be D. That is the only response with an odd number that's less than 4. And number 2, we're going to be looking for a series, we're going to be looking for an interval of convergence. So to look at an interval of convergence, we're going to go to the ratio test. And let me show you the ratio test. We're going to go to the ratio test for convergence of series, which means we're going to, if the limit is n goes to infinity of the n plus first term divided by the nth term, it converges if that limit is less than 1. The series does. The series diverges if that limit is greater than 1, and it can either converge or diverge if that limit is equal to 1. So if I want to know when those values converge, what I'm going to do is I am going to start out by saying, let's look at the limit as n goes to infinity of the n plus first term, absolute value of x plus 2 to the n plus 1 divided by the square root of n plus 1 divided by the nth term. Now, instead of writing a complex fraction, I like to multiply by the reciprocal. So instead of dividing by that nth term, I'm going to multiply by the reciprocal of the nth term. Okay. This just looks a lot neater to me, and I can work through the problem a little bit quicker. So as combining terms, the x plus 2 to the n plus 1 divided by x plus 2 to the n, that's going to be the limit as n goes to infinity of just x plus 2 times the square root of n divided by the square root of n plus 1. As n goes to infinity, this expression here goes to 1, so the limit here is the absolute value of x plus 2. Now, in order for this series to converge, I need to find out when the absolute value of x plus 2 is less than 1. Well, the absolute value of x plus 2 is less than 1 when x plus 2 is between 1 and negative 1. So x between negative 1 and negative 3 is the interval of convergence. Well, not really. Remember that part about being equal to 1 will make it either converge or diverge. You don't know which. Well, this is strictly less than 1. We know it converges on this interval, but we don't know what happens at the endpoint, and we need to check. So what happens at the endpoints, notice that at the endpoints is when the limit would be equal to 1. At the endpoints, I'm going to say, well, if I put negative 3, let me show you the function again. If I put negative 3 in here, okay, then I have negative 1 to the nth power divided by the square root of n. Negative 1 to the nth power divided by, I'm going to write n to the 1/2, right, is my sum. You can't see what I just wrote, but now you can. Now this series alternates in sign. If I ignore the signs, it's a p-series, right? In fact, when x is equal to negative 1, I'm going to get the p-series, okay, because I'll just end up with 1 to the nth power, which is 1. And this is a p-series where p is less than 1, so this actually diverges. And you see that? Now you can. That actually diverges. Now back up here, it alternates in signs. As n goes to infinity, terms decrease. Okay. And well, actually the absolute value of the terms decrease. And the limit as n goes to infinity of this nth term is 0. Therefore, this one converges by the alternating series test. So that means that my interval of convergence, I'm going to include the negative 3 and not include the negative 1. So if I go back here, my choice here includes a -3, doesn't include -1. My answer is B. Now, this is a multiple choice question, but you still had to kind of do all of this to do it, unless you could figure out a quick way. And I can't figure out a quick way tonight, so I'm not going to try to. But you will see this often on free response, and nobody's going to see all this work if you're doing it for multiple choice, but you probably needed to practice to review what to do anyway. Let's look at another example. In example 3, which actually takes up 2 pages, I think I'll just write this down and then move on, right? So we have in Roman numeral 1, the sequence 5n over 2n minus 1. Notice I said sequence. And here, e to the n over n. And Roman numeral 3 there at the top, e to the n over 1 plus e to the n. Now a sequence, it asks which sequence convergence. A sequence converges if the limit as n approaches infinity of that nth term is a constant. A sequence converges if the limit as n approaches infinity of the nth term is a constant. Well, if I look back up here, if I take the limit as n approaches infinity of 5n over 2n minus 1, that limit's going to be 5/2. This limit's going to be 5/2. So that converges to 5/2. If I take the limit as n goes to infinity of e to the n over n, well, that's actually going to have a limit of infinity. And if I take in Roman numeral 3, the limit as n goes to e to the n over 1 plus e to the 1, well, for Roman numeral 3, that limit is 1. So these two, Roman numeral 1 and Roman numeral 2, are the ones that converge. So my answer to number 3 is 1 and 3 only. So the answer there is D. Let me see if I have enough space to write on here. When you're writing with a marker, it takes a lot of space. So that's why I have this piece of paper going along with me. So now, oops, slid it up too far. Here we go. Yeah. Now for number 4. In number 4, it wants to know which of the following series converge, right? So I have in Roman numeral 1, n over n plus 2, and Roman numeral 2, cosine of n pi over n, and in Roman numeral 3, the nth term is 1 over n. Well, I know, right, in Roman numeral 1, let's just quickly look at the limit as n goes to infinity of the nth term. Okay, that's not 0. That means that Roman numeral 1 diverges. That one. Now, as n goes to infinity here and here, in Roman numerals 2 and 3, the limit is equal to 0, so that doesn't help me. In Roman numeral 2, I don't recognize that series, so I'm going to write out a few terms. Let's see, when n is 1, I'm going to have the cosine of pi, which is -1 over 1. Plus, when n is 2, I have the cosine of 2 pi over n, so that's 1/2. When n is 3, is the cosine of 3 pi, which is -1 over 3, so -1/3, and so on. Well, I look at this and I go, hey, I recognize this series, and I hope you do too. This is the alternating harmonic series. And what's special about the alternating harmonic series is it converges. the alternating harmonic series passes the alternating series test. So 2 converges. And I look at Roman numeral 3, and just by looking at the nth term without doing any work really, that's the harmonic series. And a harmonic series diverges. So there's only one convergent series, that's Roman numeral 2. So the answer to number 4 is 2 only, or B. Moving on. And number 5, there, it asked us, well, if this limit is finite, which of the following must be true? Well, this limit is just another way to write this improper integral. And according to the integral test, if I compare this improper integral to a similar infinite series, say something like that if this converges, that converges. Okay? Well, if this limit is finite, this series converges, which means that, well, that integral converges, sorry, which means that this series converges, which means that the answer is A. Notice that that problem required no algebraic manipulation, no finding anything. We really just had to know the integral test. And number 6, slide that up so you can see that. It wants to know the value of this series. Well, if you've noticed so far, there's only one type of series that we know the value of. There will be other ones where we can figure out the value of, but that's because they're special. In this case, this one is geometric series, right? First term, let's call it T sub 1, A sub 1, I don't care what you call it, but the first term is actually 4/3, and the common ratio is actually 2/3. So the sum of this series is 4/3 times 1 over 1 minus the common ratio. So 1 minus 2/3 is 1/3. I reciprocate that, that's 3. So that's 4/3 times 3, which is 4. So the answer to number 6 is C. Continuing to move on. If I can find a page, there it is. For number 7, which of the following series diverges? Now notice that we're asking for the ones that diverge and not the ones that converge. Everything else asks which ones converge. So I look at this and I say, okay, wait, Roman numeral 1 is geometric with a common ratio of sine of 2 over pi. The question is that less than 1, greater than 1, or equal to 1? I'm pretty sure that the sine of 2 is in the second quadrant, right? Because 2 is between pi, which is about 1.5, and, well, pi over 2, which is about 1.5, and pi, which is about 3. So it's in the second quadrant. That means that that number is bigger than, it doesn't matter, it's smaller than 1. Right? And that means that pi is bigger than that number. You know what? I don't even have to think about it that hard, right? The sine of 2 is smaller than 1. How about that? And pi is bigger than 1, so this fraction would be smaller than 1. So that converges. So we don't want that one. Roman numeral 2, that's a P series, where P is equal to 1/3, and 1/3 is smaller than 1. That means this one diverges. So we're keeping Roman numeral 2. And at e to the n over e to the n plus 1, which kind of looked like a series we did before, But Roman numeral 3, with a quick check in my head, the limit as n approaches infinity of this nth term is 1, and that's not 0. So that one diverges. So the answer to number 7 is 2 and 3 only, which is D. At number 8, we're looking at it. They told us it's an infinite geometric series, and they want us to find the sum again. Well, the first term is 3/2. The common ratio, see, 3 times 3 is 9, so 3 over 2 times 8 is 16, so the common ratio is 3/8. So it's 3/2 divided by 1 minus 3/8. And so that means 3/2 divided by 5/8. And that is 3/2 times 8/5. That's 24 over 10. And if I change that to a decimal, that's 2.4. So even though they had a decimal answers, I really didn't need a calculator for that. So that. And the last one, number 9, what are all values of x for which that series converges? Well, again, we're going to do the ratio test. So I'm going to take the limit as n goes to infinity of the n plus first term divided by the nth term, which I'm going to express by multiplying by the reciprocal. Now, taking this limit, this is the limit as n approaches infinity of x minus 2 times 1/3, because I have 3 to the n over 3 to the n plus 1, times n over n plus 1. The limit as n goes to infinity of that denominator is 1, of this last term is 1. So I'd be left with the absolute value of x minus 2 over 3. Now, in order for this series to converge, I know that an absolute value of x minus 2 over 3 must be less than 1. Which means that -1 and 1 must surround x minus 2 over 3, multiplying by 3, and adding 2. I'm on the series from -1 to 5. So I can immediately, without doing anything else, eliminate these two. But like I said, that doesn't tell me anything about what happens at the endpoints. Well, I'm going to kind of just point around instead of doing a lot of writing. When x is -1, if I put -1 in here, I get -3 to the n, and that's being divided by 3 to the n, which net result will be -1 to the n over n. Well, -1 to the n over n is alternating harmonic series. So it converges at x equals -1. When I put 5 in, I get 5 minus 3. 5 minus 2, which is 3. 3 to the n over 3 to the n would be 1. So I'd be left with 1 over n, which is the harmonic series, which diverges. So this E is my interval of convergence. They didn't use the word interval of convergence, but that's exactly what they're asking for here. And so let's take a few minutes and look at a couple of problems from free response, which would require us to look at an interval of convergence. Yeah, if you got your handouts from your teacher, all of the problems that I'm looking at are contained within them. So do with that information what you will, including PowerPoints are there too. All right, so from 2010, this is from the Form B exam. We're going to look at number 6. So we want to find the interval of convergence for the Maclaurin series. We're just going to look at part A. We're not going to look at part B at all. So for part A, we want to find the interval of convergence. You should just automatically launch into the ratio test unless you see that it's a geometric series or something, which this one is not. So this is the limit as n goes to infinity of 2x to the nth power, n plus 1 power, over n. Now, the reason I didn't write the -1 to the nth power part is because I'm taking absolute value, and it's either -1 or 1. So when I take the absolute value, it's going to be all positive, so I don't need the -1. Hope that made sense to you. Times the reciprocal of the n plus first term. And again, I'm not doing the -1 for the same reason I just said. So this is going to be equal to the limit as n goes to infinity of, well, 2n plus 1, 2x to the n plus 1 divided by 2x to the n plus 1 is just 2x. And I'm left with n minus 1 over n. The limit as n goes to infinity of this second fraction over here is 1. So this limit is equal to the absolute value of 2x. Now that I've found this limit, in order to determine the open interval of convergence, the interior of my interval of convergence, I need to set this limit less than 1, which means that x, oops, I went too fast, that x has to be between -1/2 and +1/2. But I am not done. Right? This just tells me where I'm guaranteed. I need to check the endpoints. These are places where that limit would be equal to 1. I need to check the endpoints to determine whether to include them as well. So checking x equals -1/2. My sum is now going to be -1 to the nth power, right? 2 times -1/2 is -1 over n minus 1, right, where n starts at 2. If I remember this correctly, yeah, this is from n goes from 2 to infinity, so it starts at 2. Now, it may not be obvious in the beginning what kind of series this is. If you don't know right off the top of your head, you could always plug some numbers in. So -1 squared is 1 divided by 2 minus 1, which is 1. So the first term is 1. For 3, I have -1 divided by 2. So it's -1/2. For 4, I have +1 divided by 3. So that's +1/3. This is the alternating harmonic series, which converges. Now, on the actual exam, when you do this on the AP exam, should you have to do this on the AP exam, you have to not only show a little bit of work, say whether it converges or diverges, but you have to say why it converges or diverges. You don't have to write out these terms, but frankly, I like to write out terms to illustrate and make sure in my mind that it is what I think it is. But you do have to say it converges and gives a reason. Now, that reason might be because it's a special kind of series, like it's alternating harmonic or harmonic. Or, especially in this case, I could have done the alternating series tests and showed that it was convergent. Now I'm going to look at what happens when x is equal to +1/2. When x is equal to +1/2, I get 2 times 1/2, which is 1, and 1 to the nth power, 1 to any power is just 1. So this is 1 over n minus 1. Now, hopefully, you'll see that, well, if that's the alternating harmonic series, this is probably just the harmonic series, and you'd be correct. And the harmonic series diverges. Therefore, the answer to the question, the interval of convergence is, C, is -1/2 is less than or equal to x, which is less than or equal to 1/2. So problems like this are usually worth 5 points. This part of the 9-point problem is most likely worth 5 points. And this is usually how it's scored. The points go down like this. You get 1 point for setting up the ratio. Now, some people set all this up before they take the limit. I do it while I'm taking the limit, but it's really for setting up the ratio, not actually setting up the limit. The second point, you get 1 point for finding the limit. That's how it usually goes. So being able to evaluate that limit. Don't be lazy with your limit notation. In order to be convinced that you're finding a limit, somewhere around in your paper, the reader is going to be looking for the limit notation. So don't just kind of just do stuff and say that it's equal to the absolute value of 2x. If I take this stuff off here, over here off, this is equal to that, but that's not equal to this without the limit symbol. So finding the limit, and 1 point for what I call the open interval. Now, remember when I said 5 points? There's the first 3. To get the other 2, you have to do this other stuff down here at the bottom, right? Checking the endpoints and stating the actual interval of convergence. Now, sometimes it's 1 point for each endpoint, or more likely, it's going to be 2 points for analysis and interval, where checking my endpoints are my analysis. They may not have the words strictly like that. They may have the points split up, but analysis and answer, endpoint justification and answer, something like that for these last 2 of the 5 points. It is very important, again, that you don't just say that this series diverges, that you give a reason for the divergence of the series. In this case, it's because I know it's the harmonic series. So that takes care of that problem. Let's look at another problem. Now I forgot which one I looked at. I looked at this one. And now, nope. Now I'm going to look at this one. This may not necessarily follow the order that they're in the packet, but they're all in the packet, okay? From 2006, this was number 6. So we told you that F is equal to that power series. We haven't told you the closed form of F, but we have told you that it's equal to this power series. And in part A, which is the only part we're going to look at, we asked for you to find the interval of convergence. Well, just like I did before, what I'm going to do now is I am going to, this is for part A, set up the ratio test. The limit is n approaches infinity of the n plus first term, where I'm going to ignore this -1 to the n power now because I'm taking absolute values, so nothing is alternating in sign. So this is going to be n plus 1. Everywhere I see an n, I'm going to change it to n plus 1. N plus 1 plus 1 is n plus 2. And then I'm going to multiply by the reciprocal of the nth term without the -1 to the nth power. So there's my ratio. Set that up, and I've set up my limit at the same time. This is going to be equal to the limit as n approaches infinity of, let's see, x to the n plus 1 divided by x to the n is simply x. And I have n plus 1 squared in the numerator and n times n plus 2 in the denominator of what's left over. That's a squared. Sorry about that. And as n goes to infinity, this fraction is going to go to 1. So the value of this limit is the absolute value of x. So that's the value of the limit. That means that x must be between 1 and -1. That's my open interval of convergence, right? The absolute value of x has to be less than 1, which means that x is between -1 and 1. Now I need to check the endpoints. So checking the endpoints, when x equals -1, when x is equal to -1, then my nth term is going to look like this. This is going to be the sum as n goes blah, 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 blah. -1 to the n times -1 to the n over n plus 1. And -1 to the n times -1 to the n is 1. So that's really n over n plus 1, which, do you know? Look at it real quick. It diverges by nth term test. I'll take the limit as n goes to infinity of that nth term. That series diverges. Ooh, I don't know what that was. I think I said series, and Siri thought I said Siri. So this is the sum as -1 to the n. I'm now going to take my other endpoint when x equals 1 of n times 1 to the nth power over n plus 1. But you know what? I don't need to do any more than that. This one diverges too by nth term test. Nth term test. I'm developing a list. A lisp. As oh geez. I'm almost finished. So that means the interval of convergence is -1 to 1, the open interval. Now you might be thinking, hey, Ms. Morton, so what happens if I stop right there and don't do anything else? You still only get 3 out of 5 points. We need to be convinced that you know why we don't include the endpoints. So you got to show the endpoint check anyway. So the 2 points at the bottom right, you know, if you remember, I said it's usually worth 5 points. You know, 1 point for setting up the ratio up here, 1 point for finding the limit, and 1 point for the open interval. Now, the open interval happens to be the answer in this case, but there's still 2 points to be had. So they may decide to say, I'm going to give you a point for checking each endpoint, but they're going to force you to check the endpoint. So don't forget to do it, even though the answer comes out to be the same as the open interval. Without checking the endpoints, you would not get full credit. I'm going to look at one more problem, and that one is going to be, not that one, this one. This is from 2009 Form B. It was number 6. It had a series question, tends to be number 6. It's not always number 6, but it's pretty close to always number 6. In this problem, we've given you this power series here. 1 plus x plus 1 plus x plus 1 squared plus and so on, right? The nth term is x plus 1 to the nth power. And in part A, they want us to find the interval of convergence. Now, what they're hoping you're going to do with this particular problem is that you're going to notice, hey, that's a geometric series, right? And since that's a geometric series, it will converge when the absolute value of x plus 1, the common ratio, is less than 1. I don't even need to check the endpoints because at 1, it will diverge. So all I need to do now is express this open interval, and I'm actually done. So I included this problem because I wanted to show you an example of a problem where I would not use the ratio test. Now, clearly, since it's had 4-part, well, maybe not clearly. From the previous examples, you see that the ratio test takes up a lot of space and it's worth 5 points. It's not going to have 3 other parts if they expect you to do the ratio test. Okay, so it was really simple if you recognize that it was a geometric series. So recognizing that a series is geometric or P-series, or even an, well, maybe not an alternating harmonic series, but a P-series will make this all really simple to figure out how to find the interval of convergence. So what did I talk about? I quickly reviewed the tests for convergence of constants that you should know, like the nth term test, the alternating series test, the P-series test, the geometric series test, the integral test, and the 2 comparison tests, direct comparison and limit comparison. You throw the ratio tests in there too. You can do that as a test for a series of constants as well. We usually use the ratio test, however, for determining the interval of convergence, but realizing that we need to check what happens at the endpoints, i.e. when L is equal to 1, to determine the actual interval of convergence and not just the interior. You should know a little bit about absolute and conditional convergence. I'll just throw this up here for you to see it real quick. I'm going to throw this up here as a quick reminder. It's not necessarily going to be asked directly, but if not this year, definitely next year when it becomes part of the new AP Calculus exam. Right? So if the series converges absolutely if the absolute value of its terms converge, right? And the series converges conditionally if it converges as you have it, but the series absolute value diverges. So an example, let's say we have a P series where P is 2, right? The sum from 1 to infinity of 1 over n squared. Well, actually, let's make it alternate. -1 to the nth power over n squared. Well, the absolute value of that is a P series where P is equal to 2. So that series is going to converge, which means that the alternating series that we talked about converges absolutely. So that it gives you an idea of what's happening now. The alternating harmonic series, for example, is conditionally convergent, right? Because the harmonic series, the series where you take if you take the absolute value of the individual terms in the alternating harmonic series, you get the harmonic series, and that diverges. So that means that the alternating harmonic series is conditionally convergent. Okay? That's just throwing that out there in case it shows up, because it is something that you're supposed to know how to do. So in my last video, my very last video on power series, I'm going to take a look at error bounds, and that includes Lagrange error and alternating series error bounds, and the Maclaurin series that you have to memorize, getting series from known series, and work mostly for response questions so that we can deal with that. And I'm going to wish you good luck on the AP exams next week. So if you have questions, you can always tweet me using the hashtag #AskMoniqueKY, or you can tweet me directly at Monique_Morton on Twitter. I will check my Twitter periodically, and if I see questions, I'll answer them. I don't see anything. I don't think anybody's watching me live, so I'm not going to worry about looking at comments here. But if you have any questions, let me know. I hope this was helpful, and I'll see you later. Bye-bye.